Good day, my name is Ilya Khrykin. I'm currently a postdoc at PUCV in Chile. Present to you the results of our ongoing work on reconstructing the distribution of cosmic baryons using the fast Fourier bursts. But first, let me give credit to many people behind this project that is shown in the bottom of this slide, as well as to mention that this work is done in collaboration with Kraft and the F4 teams. Okay, so if we consider n-body, so the dark matter only simulations, then within a well-established lambda CDM cosmology, the distribution of dark matter between the large-scale structure and the halos is well known. For instance, at redshift 0, the simulations predict about 50% of the dark matter to be in the halos. But once we consider baryons, there's a very tempting idea to just assume that baryons trace dark matter exactly, which, however, might lead to some erroneous conclusions. Indeed, the results of the hydrodynamical simulations show that the distribution of baryons is significantly affected by the stellar and AGM feedback mechanisms at low redshifts. The feedback not just influences the individual galaxy, but it also modifies the distribution of baryons in the large-scale structure on the 10% level. And this is apparent from the animation in the left bottom corner of the slide, where I show the density of the dark matter on the left and the density of the baryons on the right in SIMBA suite of hydrodynamical simulations with different feedback prescriptions. And you can see that while the dark matter density stays almost the same, irrespective of the given feedback mechanism, the density of baryons changes significantly. And therefore, obtaining the distribution of baryons observationally would be crucial for refining our understanding on how the galaxies evolve, or how feedback mechanisms work, how galaxies and large-scale structures co-evolve together. Unfortunately, the decades of heroic observational efforts have proven that getting observational constraints on the distribution of baryons is really hard. And at low redshift, that was one of the reasons for the so-called missing baryon problem. It all changed when the fast Fourier bursts were discovered. So briefly, the fast Fourier bursts, or FRBs for short, are bright millisecond transient signals of unknown nature, but now of established extragalactic origin. And the FRBs exhibit a frequency-dependent time delay of photon arrival, which we call the dispersion measure, or DM for short. This DM is caused by the free electrons along the line of sight with which the FRB signal interacts. And under a valid assumption that the universe is ionized at low redshift, these dispersion measures are in turn the direct probes of all the cosmic baryons. And what is even better, the dispersion measures don't depend on the gas temperature or metallicity, something that other observational probes often must rely on. So in 2020, McCarthy and co-authors, using the handful of then localized FRBs with measured redshifts, showed that their dispersion measures, their cosmic dispersion measures, are consistent with the baryonic fractions predicted by the lambda CDM cosmology. So this effectively solved the long-standing missing baryon problem. Unfortunately, as you can see, this huge scatter in this relation is shown by this gray area on the plot. And it's caused by the cosmic variance due to the unknown foreground structures between us and the FRB. So this large scatter prevents us from saying where these baryons are located exactly. Are they in the IGM or are they in the CGM? And so in order to overcome this problem, we developed a technique called FRB foreground mapping. Consider a path that the FRB signal follows from its host galaxy, which on this schematic image is shown on the right side, to us in the Milky Way on the left. The integrated dispersion measure can be split into four main components. The first one is the contribution from Milky Way's ISM and the halo. The second is the analogous contribution from the FRB host galaxy. Then we have a large contribution from the diffuse gas in the cosmic web on the megaparsec scale, which is termed DM-IGM, and it is a function of fraction of baryons that reside in the IGM, call it FIGM. And finally, we have a cumulative contribution from all the foreground galaxies, galactic halos, that are intersected by the FRB signal. And it is a function of the extent of the halo and the fraction of CGM baryons inside a given individual halo. And so the main idea behind the FRB foreground mapping is that the underlying density field in the foreground of the localized FRBs can be reconstructed to a very high precision by measuring the large-scale distribution of galaxies in front of the FRBs. Henceforth, we claim that we can beat the cosmic variance and precisely identify where the cosmic baryons are located. So more precisely, the foreground mapping consists of two main parts. First one is the wide field spectroscopic survey, which records the redshifts and coordinates of the galaxies between us and a given FRB. Because galaxies are biased tracers of the density fields, we can then use this wide field distribution of galaxies to perform the density reconstructions. And second step is the narrow field spectroscopic survey, which is required to identify the galaxies and groups whose halos are intersected by the FRB signal. So first we tested our technique on the mock observations, and this is published in KG Lee's paper in 2022. For that, we have utilized the Millennium simulations and associated Enrique 2015 galaxy catalogs. So from these catalogs, we extracted the galaxy positions, their redshifts, and their properties in the foreground of some number of mock FRBs. We then used a Bayesian density reconstruction called Argo to get the density field along the line of sight of these mock FRBs. So in the bottom here, I show the plot, an example of reconstructed density field using Argo, as traced by these galaxies extracted from the Enrique catalogs. The galaxies here are shown by the black dots. So we can kind of look into more details on this. And this plot gives you an example of what kind of DM-IGM values one would expect from these density reconstructions as a function of FIGM. But what is even better is that Argo, being explicitly Bayesian code, it doesn't give you only one density realization, it doesn't give you one answer, it gives you actually multiple realizations, which can be used to estimate the associated uncertainty. And so the plot and the animation shows how the distribution DM-IGM from density reconstructions depends on the fraction of baryons that reside in. It's basically just a multiplicative constant. And the last thing that is left to do is to actually check if our method using density reconstructions is doing better, is performing better than just a Mahat relation in terms of recovering the DM-IGM values. And so the plot on the top right corner shows you basically the Mahat relation in the Millennium simulation, and its comparison to the values of DM-IGM that we got from Argo. Those are shown by the blue arrow bars, and the true values are shown by the red crosses. So you can see that we can actually, by using Argo, we can do at least 2-3 times better than just using the global statistic, which is the Mahat relation. So in addition to the mock wide field galaxy catalog, we extract galaxies within 10 arc minutes of each FRB sightline. And for each of these galaxies, we use the modified NFW profile to estimate their contribution to the total dispersion measure. So these contributions depend on two model parameters, as I mentioned before. So the extent of the galactic halo in units of R200, which we call Rmax, and the fraction of CGM baryons inside the individual galactic halos, which we call F gas. So we also take into account the highly uncertain halo masses, and for each galaxy that we find, we sample the corresponding distribution centered on the mean halo mass, and we assume a 0.3 DAC sigma. And once again, the significance of measuring the F-gas can be seen from this plot from our recent paper, which shows how the F-gas changes in SIMBA simulations depending on the different feedback prescriptions. So this slide just to show you, to illustrate how the inferred distributions of the DM IGM and DM halos in each FRB sightline depend on our model parameters, F IGM, F gas, and R max. And finally, to predict how accurately we can measure our model parameters, we have performed the Fisher matrix forecast, where for each mock FRB sightline, the model DM is given by this equation, where in the first term, this averaging comes from all the realizations of the density field for a given FRB. In the second one, the averaging is done over the different realizations of the halo mass. So you can see that our Fisher forecast showed that we can constrain the FIGM and F gas to about 10 to 15% precision with just 30 FRBs, 30 localized FRBs. And in contrast, on the right side, you can see the constraints that you would get if you don't use the foreground mapping technique, if you just use basically the mark-out relation. So you can see how the arrow bars are blow up. So that's an evidence of that we are on the right track. And so based on these promising results of the mock analysis, we have initiated the FLIMFLAM spectroscopic survey, which is aimed at delivering the samples of galaxies in the foreground of about 30 FRBs. For that, we primarily use the 2DF omega spectrograph on AAT telescope for the wide field observations. For the narrow field observations, we used also AAT, and we supplemented it with data from KEAC and VLT, as well as some archival data from SDSS and 6DF. Here's an example of the 2D distribution of galaxies in the foregrounds of two FRBs as observed with AAT. And this will be also published soon in Yuxin Huang's paper. And so I'm happy to tell you that the first data release and the analysis of 8 FRB sightlines is out. We published it this year. So the bottom table shows you the 8 FRB sightlines that we chose, and the rightmost column tells you how many galaxies we found that we used in the density reconstructions. And here's an example of a single realization of the density field reconstruction from Argo using the galaxies that I just mentioned. So the first 4 FRBs in our sample are at very low redshift, and they have SDSS and 6DF coverage. That's why these plots are so crowded with black dots. Each dot is a galaxy. But if you go to a higher redshift, so the second part of the sample, there's only AAT data available for the wide field and so so here's an example of what you get from AAT. From all these density reconstructions, we estimated the corresponding DM-IGM distributions for each FRB sightline that I show on this plot. And the bottom panel just shows you the mean and the corresponding uncertainty of these distributions from the top. So the next step was to acquire the information on intervening halos using the narrow field observations. And this plot shows you all the galaxies and groups that we found in each FRB sightline. So here, each circle illustrates the size of the halo, assuming these halos extend to 1 R200. And obviously, I should emphasize that the sizes of the circles make sense only along the y-axis. And this is done for visualization purposes. And so, again, note that this plot is done for the mean halo mass of each galaxy, and if we actually include the uncertainty, the associated uncertainties, we can estimate the corresponding DM halos distributions in each FRB field, which are shown on this plot. So we can now write down our model DM, which looks very similar to what we use in the Fisher matrix forecast, except for the R1, we have decided to fix the Rmax to just one R200 due to the admittedly limited sensitivity of such a small sample. And we also split the contribution to the DM from the FRB host galaxies into the corresponding contribution from the halos and the unknown component associated with the ISM or the FRB progenitor itself, which will be our third parameter. And DM host halo, this part is also estimated from using the modified NFW profile. And then we can write our standard Gaussian likelihood, where we take into account the uncertainty in all our DM terms. And we can proceed to sample this likelihood with the MCMC to get the constraints on our parameters. And I present you the results of our MCMC. So as you can see that we measure the fraction of variance in the AGM to be about 60% plus minus 10. The fraction of CGM variance in the halos is a bit unconstrained, I must say, but we do also a good job in constraining the unknown contribution from the ISM of the host galaxies, as well as the total contribution from the host galaxies of the FRBs. And given this constraint on FIGM in particular, we can roughly compare it to the results of the hydrodynamical simulations, which are shown on this plot. Just a few examples of the distribution of variance in the SIMBA simulations, dependent on different feedback prescriptions. And this the red dot is our constraint on FIGM. So it's our results kind of favor the no feedback model at the moment, but given our large error bars, I wouldn't jump to any conclusions. So again, our sample is limited, but we're continuing our work, and we hope that the second data release, which should be ready sometime next year, I hope. So the second data release should be able to, I hope, definitely say something about the feedback. So I'm going to leave you with my conclusions, and if you